Hello, this is Nate Lohmeyer. Welcome to Tempo ePortfolio Project 2. This is problem 1. A mass of 15 kilograms of air in a piston cylinder device is heated from 25 to 77 degrees Celsius by passing current through a resistance heater inside the cylinder. The pressure inside the cylinder is held constant at 300 kilopascals during the process, and a heat loss of 60 kilojoules occurs. Determine the electric energy supplied in kilowatt hours. Okay, so in this problem, the resistance is heating the air inside the piston cylinder device. As that air warms up, that piston is going to rise. The pressure inside, we're being told, is being held constant. There is also some heat loss. So we have two states. State 1. State 1, where T1 equals 25 degrees C, which is equal to 298 Kelvin. P1 equals 300 kPa. State 2, T2 equals 77 degrees C, which is 350 degrees K. And P1 or P2, excuse me, is still 300 kPa, since it's a constant pressure situation. We know there's a heat loss of 60 kilojoules, so that's Q out. Okay, so first is our energy equation. E in minus E out equals delta E system, which from our formula sheets we can write Q in minus Q out plus the work in minus the work out equals the change in internal energy plus the change in potential energy plus the change in kinetic energy. Since the entire system isn't moving, we can neglect kinetic energy and potential energy. We can also, there's no heat coming into the system apart from the work being added to the system, so we can get rid of that. And then there is Q out. There is the work, the electrical work coming in, and then there's the boundary work of the piston moving. So we're wanting to solve for this electrical work coming in here, so we can do a little bit of rearranging. So the work in is equal to the change in internal energy plus the boundary work plus Q out, which they gave us for the system. We also know that delta U plus WB boundary work is equal to delta H. So our work in is equal to delta H plus Q out. Alright. So just to rewrite here, W in is equal to the mass times H2 minus H1 plus Q out. So we saw on our previous slide at states 1 and 2, they're both defined with temperature and pressure for each state. we're told that it is air. There's no liquid at all inside, so we can treat air as an ideal gas. Looking at table A17 for the first state of 298 degrees K, we can get our H1, which is equal to 298.18 kilojoules per kg. Sorry about that. And our H2 is 350.49 kJ per kilogram. So now I think we've got everything we need to plug in some numbers here. So work in equals 15 kilograms times H2 minus H1, so 350.49 minus 298.18, and that value is kilojoules per kg, plus Q out, which we're told is 60 kilojoules. Doing the math, WN equals 845 kilojoules. However, we're not done yet because the problem wanted the answer in kilowatt hours. So to convert kilojoules to kilowatt hours, we take that answer times 1 kilowatt hour per 3,600 kilojoules, and we're left with a final answer of 0.235 kilowatt hours.